Hello, everyone. We're going to continue talking about chapter 2. Good. So let's recall what we were doing. We defined sequences. So at the end of last lecture, we motivated the study of mostly series. So we talked about weird things that can happen when we consider the sum of infinite number of things. And today, what we're going to be doing is talking about sequences in more detail, specifically convergence, which will be the central topic here. So let's go to the page. So last class, we defined what a sequence is. So let me just write a little recall here. Recall that a sequence, we write it like this, AN, is a function f from the natural numbers to the real numbers. And we write AN as the image of the nth element, right? So instead of saying f of 1, f of 2, f of 3, f of 4, we avoid talking about the f and we simply list the elements, right? So quick example here. Example, if f of n equals n squared, then the sequence is, and we can list the elements, is 1, 4, 9, 16, 25, 36, etc., right? Specifically, these are 1 squared, 2 squared, 3 squared, 4 squared, 5 squared, etc., right? Or in general, we could write it like this as well, n squared from 1 to infinity. Okay, so we talked about this last time. And today we'll talk about the fundamental concept that we care in this class, which is convergence. So here's definition 2.2.3. We say that a sequence, AN, converges, that's the new word we're learning, converges to a real number, A, if for every epsilon greater than 0, there exists some capital N, a natural number, such that whenever and little n is bigger than capital N, it follows that AN minus A in absolute value is less than epsilon. All right. Now, remember, well, okay, I'll provide my observations in a moment. Let me finish this up. We write lim of AN equals A, or AN arrow A, or this one, which is a bit more precise. But in our book, I like our book because it's very concise. So if there is no need to have extra symbols, then we don't have extra symbols, so that everything is written in a nice, straightforward way. So our book actually writes this, lim AN, right? It's clear because there's no other variable. It's clear that it means when it means that n is getting bigger, right? When n goes to infinity. So they don't necessarily write the n goes to infinity because it is kind of superfluous, right? It's not needed. But if you want to write it, that's fine. There's not an issue there. And then what we need to understand here is that, I mean, this definition like this, so well, maybe you're an algebraic person, and in which case this makes perfect sense to you, right? It's just a definition with quantifiers. So it's for every epsilon, there exists an n, and then some inequality that involves absolute value. But for the rest of us, those of us that think better with pictures, it makes more sense to understand what is the meaning of this, right? And we talked about this before, that the absolute value is a clever way of talking about the distance between 2 points in the real line. So this is an algebraic way of saying the distance from AN to A is less than epsilon. Okay, and I encourage you to think of it that way. I'll supply another definition in just a moment, which is the same. It's just like a rephrasing of this definition. But before, let's actually write it in the shortest possible way. So here is rephrasing in a purely symbolic way of what this definition is. So AN converges to A. This is the definition that I'm writing right here. Let's see it. Is for every epsilon greater than 0, there exists some capital N in natural number such that if little n is bigger than capital N, then AN minus A is less than epsilon, right? All of this line over here is the symbolic way of the convergence definition we just learned. For every little epsilon, there is some capital N, such that for every little n bigger than capital N, this happens, okay? And now we're gonna restate it, like I said, in a more geometric way, with in a way that we can draw pictures, which is probably what you're gonna try to do when you want to prove anything about convergence, okay? So to begin with, let's write down this useful definition of what we're gonna be calling a neighborhood, or more precisely, an epsilon neighborhood. So here is what it is. Given a real number A and little epsilon greater than 0, we're gonna define this V sub epsilon of A. And we read it as the epsilon neighborhood around A. And it is precisely this. This consists of the real numbers such that x minus A is less than epsilon. Now, this is a fancy way of saying the following, if you think about it. So if I were to make a little picture, maybe now is the time. So here's the real line. Now remember what we talked about. This means the distance from x to A is less than epsilon. So somewhere over here is A. And what we're saying is pick the points that are within epsilon of A. That means I go epsilon units this way, and I go epsilon units this way, and I include everyone in between except the endpoints, because this is strict, right? So it's all of these, everything from here to here without including the endpoints. So a way easier way of writing this is just to write it in an interval notation. That's just A minus epsilon, A plus epsilon, right? Open on both sides, because we don't include the endpoints, right? So in an even shorter way, it's just an open interval of a radius. If you want to think of radius, I mean, I know it's not a circle, but if you wanted to, it could be like a circle, the equivalent of a circle in 1 dimension, right? A circle is in 2 dimensions, a sphere is in 3 dimensions. So this type of interval is like a circle in 1 dimension. And it's kind of like the circle centered at A of radius epsilon, right? So we don't call it a circle, we call it the epsilon neighborhood of A, right? Or center at A. This is called the epsilon neighborhood of A, or centered at A, to emphasize the fact that A lies right there at the center, right? Okay, and then we could use this definition to rephrase this neighborhood, to rephrase our definition of convergence, okay? And that's what we're gonna be doing next. And the book calls it the definition 2.2.3 part B, or is it? Yeah, but it's the same definition. Is we're just writing it in a different, with a different language, so to speak. All right. So let's write it here. Is this definition 2.2.3 part B. It's the same definition of convergence. In fact, let me try to see if we put them like this so that you see that I'm doing the same thing. All right. And this is what it says. It says a sequence AN converges to A. So this first part is the same, of course, if for any epsilon neighborhood of A, V epsilon A, there exists a point in the sequence. This is the capital N, after which all of the elements of the sequence are in V epsilon A. Okay, let's see if this makes sense. I mean, we have it written down, the one over here on top. So for every epsilon, see, if for any epsilon neighborhood is what it says over here, there exists a point in the sequence, that's the capital N, there exists a capital N, after which all of the elements of the sequence are in V epsilon of A. So that means after this would mean a little n, which is bigger than capital N. And if this happens, if AN minus A is less than epsilon, that means the AN is in this epsilon neighborhood, right? So in other words, the picture you should have in mind is the following. So we have a sequence, we have our A, and we have we're giving some epsilon. We need to do it for every epsilon. So here's the epsilon neighborhood. This is B epsilon of A. And we say this is gonna work if at some point the elements of our sequence are all in here, right? So maybe at the beginning the sequence is here, then here, okay, let me call it A1, A2, maybe A3 is over here, maybe A4 is inside, but then A5 goes away, and then A6 goes this way, and then A7, and then A8 maybe over here, I don't know. But it's, eventually, all of them start falling in here. A9, A10, A11, 12, 13, 14, 15. All the rest are inside here, right? At some point, all of them come into this neighborhood here. In this case, it happened after after 9, right? So in this little example that I just drew over here, the capital N was 8, because any member after the 8th one, any point after the 8th is already inside this little neighborhood. Okay, does that make sense? So you can even write it without the N. So you can say it like this: every epsilon neighborhood of A contains all but finitely many members of AN. That's like a one-sentence definition of convergence, right? AN converges to A, so this is a way of writing AN converges to A if every epsilon neighborhood contains all the members except finitely many. So the finitely many in this case are these ones that are outside, right? These A1, A2, A3, A5, A6, A7, and A8. So those are, in this little example that I drew here, the finitely many ones. Okay, is that clear? Is it clear how those two definitions are the same, really? So it's yeah, go ahead.
It's sort of confusing a little bit, like how does n equal 8 relate to a and converges to a?
Well, see, we'll do some examples coming right now, because I haven't proved that I mean, in this picture, we only did it with this specific epsilon, right? I picked this epsilon over here. I don't know what it is, because I didn't put a scale on my axis. But whatever this epsilon is, for this epsilon, this n works. If I give you a different epsilon, right, if I make it even smaller here, then maybe you need to pick a bigger n. So this is important. The entry point, let's call it let's call capital N the entry point, right? So this capital N is when you for sure can guarantee that everyone after that is inside, right? And that entry point may change depending on what epsilon is. Maybe if your epsilon is too big, well, you pick an N that is easy, like in this case 8. But if I make my epsilon super tiny, if my interval becomes super tiny, now maybe I need to pick a super big N so that I can guarantee that all of them are inside.
So, Professor?
Yes.
So the n is like the index of how far you have to go in the sequence?
Precisely. Yes. You couldn't have said it better. Yes, that's exactly what it is. The capital N is the index after which every element is guaranteed to be within epsilon of what we believe the limit is, what the A we think is the right one is. We'll do some examples. This will probably clarify it, and that's exactly, and I'm gonna then show you actually, it's written in the book, so sort of like a general guideline of how you can show convergence in general.
So it's saying except the finite members, because like there has to be a point where it's in epsilon, right? So that's why you can count like how many are not in it.
Yes, exactly. So the finitely many members are the guys that were excluded, the guys that were left out of the interval. Yes. Let's see an example, and let's start with something familiar to us. For instance, what about the sequence 1 over root n? So this is example 2.2.5 in the book. And let's consider this sequence, the limit of 1 over root n, right? So the sequence is 1 over root n. And we all took calculus, so we learned how to do these types of limits. So we know what happens, right? I mean, this is getting bigger and bigger. And when we take the square root, it becomes a little smaller, but still really big. And then when you divide 1 by a really big number, should be becoming smaller and smaller and smaller. So we know this limit should be 0, right? That's the intuitive feeling. And that's how you did it in calculus. So in calculus, the way you thought about this is the number that these guys are getting closer and closer to, right? That was the way we define it, but that was imprecise. Now we're doing it like the correct way for mature, advanced math majors, right? What exactly is the meaning of this? Well, if this is, for this to be true, we need to show the following, right? Let me write it down. We need to show that for every epsilon greater than 0, there is some capital N such that And then you can say it in the two following ways. You can say it that either if little n is bigger than capital N, then 1 over root n minus 0 is less than epsilon, right? That this is the xn and this is the a, because in this case the limit we think it is 0. Or you can say it for n greater than n, 1 over root n belongs to the epsilon neighborhood around 0. These two things say the same thing, right? Or in other words, this capital N is the entry point that works for the epsilon neighborhood around 0. Okay? So as practice, let's do it not in general, but let's play this game with a specific epsilon. All right? So let's pick a specific epsilon. Like let's try to do it with, so for practice, let's pick 1 over 10. That's a tiny number, right? 0.1. Okay, so here's our picture. So here's the real line. Here's 0. And we're going 1/10 in this direction. So this guy is 1/10 and this guy is negative 1/10. And we need to show that everybody eventually comes inside here. Everyone in the sequence, except for finitely many, right? Yeah. So let's analyze where our values are. So where is A1? Well, A1 is 1, right? So let me write a few. A1 is 1 over root 1, so that's 1. So that one doesn't work. That one is very far away over here, right? Somewhere over here. Well, I mean, even farther, but A1 is farther away. A1, somewhere there. Then you have A2, right? 1 over root 2. And that's slightly closer, but still far away, etc. Till A3, 1 over root 3, A4. That one is easier to see because square root of 4 is 2, right? So this guy is 1/2. Still far away, right? So A4 is over here, far away. So at which point will these guys come inside and never leave, right? At which point will these numbers, 1 over root 10, become inside this part? That's what we need.
101.
Good, 101. Yeah. So let's check A100. A sub 100. What is that? Well, that's 1 over the square root of 100, correct? So that's 1/10 precisely. So this guy is precisely A sub 100, right? But that doesn't work yet because we need to be inside the interval, right? So that one doesn't work. And someone said 101, right? Who said that, by the way? I can see the screen right now.
It's AIM.
Ah, great. That's right, AIM. So 101. So if we pick A sub 101, that's going to be 1 over the square root of 101. And this number is bigger than 10, right? Because the square root of a bigger number is even bigger. So this number for sure is less than 1 over the square root of 10, of 100, I mean, which is 10. So this number works. This number A sub 101 is already over here. It's already inside A101. What about the ones after that? Would they also be in here? Or because we don't want them to maybe get closer and then leave, right? That would be bad. We want to guarantee that all of those elements at some point will fit inside the interval from negative 1/10 to 1/10. Would it work? So it's really, so in other words, we're saying that, so we believe n equals 100 works, right? Meaning if you pick anything bigger than 100, it's going to work. Is that true? And the answer is yes. And this is how you can guarantee that it works. See, here's what you can say. I'll write it here. We believe N100 works. This is indeed the case. And here's why. Because if you pick a little n that is bigger than 100, right? Then when you take the square root of n will be bigger than the square root of 100, correct? Because the square root is an increasing function, and this guy is 10. And then if we then take reciprocals, this means that it means that 1 over 10 is bigger than 1 over root n, right? When I take reciprocals. And that's exactly what I wanted, right? I wanted that every element bigger than 100 satisfies that this is less than 1/10. And it's also bigger than 0 because the square root is positive, right? So this happens. So this means for sure it will be, if I go back to my picture, it will be for sure between 0 and 1/10. So for sure it will be inside this epsilon neighborhood. So this means that 1 over root n belongs to the 1/10 neighborhood around 0, right? And it happens for all the numbers bigger than 100. So we won, right? We won this game when epsilon is 1/10. Now, here's the problem though. This is not enough. It's like the question that I got earlier about the picture, right? This only shows that with 1/10, if we pick epsilon equal 1 over 10, we made it work. But what if it doesn't work with other epsilons? We need to check for every epsilon. So again, just to familiarize ourselves, let's try another epsilon. Let's try one that is probably harder, right? So what if we try something like, now let us try epsilon equals, say, 1 over 100, right? That's even smaller, right? So if I look at my original picture, now I need to make it, so if I, here in my original picture, if 1/10 was here, then 1 over 100 is gonna be over here, right? Super tinier now, right? So now A100 and then A101 is not gonna work, right? So now, so what you need to do is find the entry point. When would it happen that my elements of the sequence fall inside my new interval, right? So new picture here. Now maybe we magnify so that we don't need to squint. So now this is 100 and negative 100. How far should I go in the sequence to guarantee that everyone fits in here, that all the elements are in here, right? Okay. And so what do you think? So the question is, how did we know that here the one that worked was 100, right? That's the question we should be asking ourselves. And if you looked at the argument here, the argument was 100 worked because when we took its square root, we got 10. So maybe we're lucky like that if we look now for a number whose square root would be 100. What number has as its square root 100?
100,000.
100,000, I think you went a bit too far. 10,000, yeah. So 10,000, right? And the argument is going to be the same, right? This time n equal 10,000 works. Here's the argument. I mean, it's going to seem repetitive, but that's the idea, that you get used to this by looking at it several times. Why does 10,000 works? Well, because if n is bigger than 10,000, then square root of n is bigger than the square root of 10,000, and that's 100. And then this means, on purposely even writing it the same way, so you see that is the same argument. This means that 1 over 100 is bigger than 1 over root 10, which is bigger than 0, which means that 1 over root 10 belongs at the 1 over 100 neighborhood centered at 0. Okay, now look how different was this, right? So to make it work for 1/10, we only went as far as 100. But to make it work for 1 over 100, we had to go way farther, right? So the first 9,999 elements of the sequence, actually the first 10,000 elements of the sequence don't work. You need to be bigger than 10,000 to make it work. So A sub 10,001 finally comes inside the interval, and after that, all the elements fit in there. Okay? All right. So now, for the real argument here. So we haven't really proved this limit yet. Okay? We just provided like a suggested way of approaching this problem. To really prove it, now we need to do it for an arbitrary epsilon. So how do we do that? How can we, for any epsilon that you give me, do this? Okay, find the capital N. So now let's try to do it in general. So in general, let epsilon greater than 0 be arbitrary. Think of this as the 1/10 or the 1 over 100. So which should be the capital N that we need, right? And think about what we needed, right? So here is, usually you start with what you want to figure it out, right? So what is it that we want? So here's the discovery phase is what I call it. So let's put it here, discovery. How do we discover the entry point? So this is what we want. We want 1 over root n to be less than epsilon and bigger than negative epsilon, right? To be between negative epsilon and epsilon. That's the absolute value thing, right? In fact, okay, let me backtrack a little bit. Let me backtrack to be really, really precise here. We want 1 over root n to belong to the epsilon neighborhood around 0. That's the same as 1 over root n minus 0 being less than epsilon, which is the same as negative epsilon less than 1 over root n less than epsilon, which is the one that I initially had written. Now, the part on the left, it's for granted that we don't need to care about this left inequality because this number is positive all the time, right? This number is greater than 0. So this we don't need. This one we get for free. We already know 0 is less than 1 over root n. So that one, we get it because 0 in turn is bigger than negative epsilon because this is a negative number, right? So this, thanks to this one, we're done with the left side. So the problem is the right side, okay? So what we want is, what we really want, the one that really has the meaty part of the argument is this one, 1 over root n less than epsilon. So what n would make this work? And here's what you can do, right? You could sort of like find out a relationship for little n, right? Because this is a relationship for epsilon, and you want to transform it into a relationship for little n. The way I could do that is I can first square it to get rid of the square root, which nobody likes. So this is equivalent to 1 over n less than epsilon square, right? And then I can solve for little n. So it would tell me 1 over a epsilon square less than n, okay? And this is the one that tells me what I want. It tells me if a little n is bigger than this number, then it's gonna work, right? So, perfect. So now I just discovered what capital N could be. Capital N is going to work as long as it's bigger than this, okay?
Do we need to state like Archimedes' principle to say that there's always another n that would fit that?
Yes, exactly. That's the next thing I was gonna say. So how do we know there is an integer, a positive integer, bigger than this number? And that's the Archimedean principle, right? So by the Archimedean principle, I never know if you capitalize Archimedean or not. Technically, it's an adjective, so probably shouldn't, but it's from someone. So by the Archimedean principle, there is capital N such that capital N is bigger than 1 over epsilon square, right? That for sure we know. And then that's the capital N we're going to use. All right. So we use that capital N, and we need to check that it works. Okay. So all of this was the discovery. Okay. This is not the proof. If you write this, we're going to get in trouble, you and I, because here you're proceeding like backwards, right? This is the way you discover what is the capital N that you want. Now, here is the write-up of the proof, okay? Here is the write-up. Here's how you do it, and we'll talk about the general structure of these proofs in a moment. So what you're going to do is first start with an arbitrary epsilon. So here's finally the write-up for the proof. You pick an arbitrary epsilon. Camera a little bit better. Okay. So we pick an arbitrary epsilon. Let epsilon greater than 0 be arbitrary. Then we say what capital N is by the Archimedean principle. There is capital N such that capital N is bigger than 1 over epsilon squared. And then we check that this capital N works. What do I mean by that? We have to check that if you pick an element in the sequence which is after this capital N, then that element in the sequence is already in the epsilon neighborhood around 0. So that's what we're going to check now. So let little n be bigger than capital N, right? Then little n is bigger than capital N, which is bigger than 1 over epsilon squared. Taking square roots, we get root n is greater than the square root of 1 over epsilon squared, which is 1 over epsilon, and then multiplying by the reciprocals, obtaining the reciprocal statement. This tells that epsilon is greater than 1 over root n. Perfect. And obviously, 1 over root 10 is greater than 0. So we are done, right? So thus, 1 over root n belongs to the epsilon neighborhood around 0, because it's between negative epsilon and epsilon, right? If you want, you can write the negative epsilon here. It's not going to hurt. And that's it. This is, you see how short this is? It doesn't look difficult at all. Of course, if this is the first time you read a proof and you read this, you're like, okay, yeah, this is true. Yes, Archimedean principle. Yes, I pick this little n bigger than capital N. Yes, this happens. Yes, square roots, this. Yes. Okay, yeah. Oh, sure. But then this doesn't help you recreate the proof, because the real question here is, how did they know to pick 1 over epsilon squared, right? That's the meaty substance of the proof here. How do you find this 1 over epsilon squared? And fortunately for you, you know how. You do this part that we did before, the discovery part. You sort of start with what you wanted, and that way we discovered the inequality we needed. Okay? Oh, right. We'll do more examples. Okay, if you still find this complicated, I'm not surprised. That's exactly how it should be, right? But let me show you a page in the book where we have a general template of how these proofs go. This is in page 45. Good. 45, and here it is. It says template for a proof that xn approaches x. And here it is. Your proofs should all look like this. You will always start with let epsilon greater than 0 be arbitrary. Then this is a harder step. Like it says over here, demonstrate a choice for capital N in the natural numbers. So in other words, find the capital N. Now remember, the capital N may depend on epsilon, like the one we just did, right? Our capital N was any natural number bigger than 1 over epsilon square. So it depended on epsilon square, right? On epsilon, because we had to pick something bigger than 1 over epsilon square. And like it says right here, this step usually requires the most work, almost all of which is done prior to actually writing the formal proof. They're precisely talking about that discovery box that I did, okay? And then next, once you know what is that capital N that you think is the one that's gonna work, you show me that it works. How do you show me that it works? You start by saying pick little n bigger than capital N, and then if you chose the capital N appropriately, you should be able to obtain this inequality, right? That xn minus x is less than epsilon, which is equivalent to xn belongs to the epsilon neighborhood around x. Okay, so let's put it in practice with a second exercise. Just since I have the book, it's exactly this one, that one. So let's do this exercise, 2.2.6. So let's prove that the limit of n plus 1 over n, that sequence, is 1. Show that the limit n plus 1 over n is 1.
Professor, we can't see your writing.
Yes, I know. I'm copying it from the. I'll change to the screen. But thanks for letting me know. Here is the one we want to do. Okay, so the discovery first, right? So here's the discovery. How to find the capital N, right? So we're gonna have some epsilon. So this guy is arbitrary. And then what we want is n plus 1 over n minus 1 to be less than epsilon, right? And what we should do is try to reverse engineer this to find out the capital N. For little n bigger than capital N, so need to find capital N. Okay, how do we do that? Well, let's make sense of this expression, right? What is this expression? Well, this expression is n plus 1 over n minus n over n, right? So in other words, it's just 1 over n. Yeah, I don't need the absolute value bars, right? Because it's when you cancel the n's, it's 1 over n, and 1 over n is positive, so I don't need the absolute value bars. So this is the same as 1 over n. That's not too bad, right? So 1 over n is less than epsilon is what we want. So what should be the capital N that works? And like I told you, what you need to do is to make it about n, because right now this is about epsilon. So right now we have 1 over n less than epsilon. So we want to make it about n. So the way we do that is we make the reciprocal statement here. So that we divide by epsilon and multiply by n. And this is the same as 1 over epsilon greater than n. I mean, less than n. So that this suggests the capital N we need, right? This is telling us, hey, it's going to work as long as you pick a capital N that is even bigger than 1 over epsilon, right? So this suggests capital N bigger than 1 over epsilon will work. Okay, good. So that this is the discovery. Remember, this is like the work you do backstage, right? The stuff that nobody sees. And now we're gonna do the part that you show the world. Okay. So here's now the write-up of a proof. Proof. Let epsilon greater than 0 be arbitrary. We always start with that line. Then you say what the capital N is. So set capital N greater than 1 over epsilon. And you can, if you're nice, you can tell me how you can find this. This is guaranteed by Archimedean principle, right? We can always find a natural number as big as we want. That's what we want one that is bigger than 1 over epsilon. Okay, then you pick a little n bigger than capital N. So suppose that little n is a natural number such that little n is bigger than capital N. And now what we need to do is show this inequality over here. And usually what you're gonna do is use your discovery work backwards. So you're gonna start from here, and from here go here, and then from here go there. All right? So let's see if it works. So then this is what we have. We have that little n is bigger than capital N. I forget in my definition, was it strictly greater than or equal? Let me check. It was greater than or equal here, right? Not that it matters, but, and then n is greater than 1 over epsilon. So we have that, okay. And then you see we're here, right? So then from here, we're gonna go here, and then from here, we're gonna go here. Then this happens, which is equivalent to epsilon greater than 1 over n, right? If you multiply by epsilon and divide by n. And then so finally, note that 1 over this expression, n plus 1 over n minus 1, is the same as the absolute value of 1 over n, which is, equal to 1 over n, which is smaller than epsilon. And we are done, right? Let's check that we're done. For an arbitrary epsilon, we found a capital N that makes it so that if little n is bigger than capital N, the difference of the element in the sequence minus the limit that we want is less than epsilon. Perfect, we are done. This precisely shows that the limit of n plus 1 over n is 1. So that sequence converges to 1.
Professor, how'd you get epsilon greater than 1 over n again?
From here. So this n is bigger than 1 over epsilon, right?
Mm-hmm.
So then let me do the side work here. So here's what you're doing. You first multiply, so you multiply both sides by epsilon over n. Epsilon over n times n greater than 1 over epsilon. And when you do that, what do you get? You get this one, right? This over that, the n's go away, you get epsilon. And this times that, the epsilons go away, you get 1 over n. And this is non-zero. This is important, right? And then positive. Be careful when you multiply inequalities, sometimes they flip, right? You need to make sure that you multiply by something positive and that you're not dividing by 0. So here we're fine because epsilon is positive, and I'm dividing by n, and n is greater than 0, so it's not 0. Good. Any other questions? Okay, let's do another example, but before that, we have the following definition, which is what happens when a sequence does not have a limit, right? And in that case, we call it that the sequence diverges. So we have this little definition here. Oh, well, actually, there's something before this. Let me write it here. It's theorem 2.2.7. I'm not going to prove it here because it's one of your homework problems. but it says if the limit of a sequence is unique. The limit of a sequence, when it exists, must be unique. That's important, right? So when we have a sequence that converges, it must be convergent to a single thing. It's not okay to be convergent to different things. This, of course, requires a proof. It's not a difficult proof. And if you think about it, almost from the picture, it should be kind of easy, right? My hint to prove this would be the following. Suppose that a sequence has two limits. So that means that eventually you can get within all the elements are around a little interval around one of the limits, and also around a little interval around the other one of the limits. And if your intervals are like my fingers are showing right now, when they don't have an overlap, that's impossible, right? How can you have all the elements here within my two fingers on my right hand and simultaneously here within my two fingers in my left hand? That's impossible. So the only thing you need to make sure is to choose them so that they have no overlap, because if there's a little bit of an overlap, then you can make it work. So that's my hint for that one. So let's then let me write this definition before we consider another example. So here's a definition 2.2.9. It says that a sequence that does not converge, a sequence that does not converge is said to diverge. And then we call it a divergent sequence. Good. So let's do another exercise, another example. So this is example 2.2.8. And we're going to consider a funny sequence here. Here's how this sequence is defined.
Professor, could you move your paper up just a little bit to see the theorem?
Sure.
Thank you.
Is 1, negative a half, and then 1/3, and then negative 1/4, and then 1/5, and then negative 1/5, and then it sort of gets stuck there. 1/5, negative 1/5, 1/5, negative 1/5, 1/5, negative 1/5, and you get the pattern, right? So that pattern continues after that. It's 1/5, negative 1/5, 1/5, negative 1/5, etc. Right? So, so now let me ask you the type of things we haven't done yet. So we showed a couple of examples to see how to check if it was convergent, right? Now here, let's start with trying to show that this series is not convergent to 0, right? Or let's start with something, let me see. How about not being convergent to, is it 1/5 first? Well, let's start that it's not convergent to 0. So show this sequence is not convergent to 0. Okay, how do we do that? Well, we need to check that the definition fails, right? So what is the meaning of the definition failing? Means there is no way that eventually there is no interval, so we need to show that. So let's take a look at the definition again. So the definition, remember, so being convergent to 0, I'm going to write it here. AN converges to 0. It means that for every epsilon, there is some capital N, such that if little n is bigger than capital N, then AN minus 0 is less than epsilon, right? So this is that it is convergent. So what is, how do we negate something like this, right? How do we logically say that this doesn't happen? And hopefully you remember from 320, right? When we have quantifiers, the existential quantifier becomes a universal quantifier, and the universal quantifier becomes an existential one, and then you negate the inner statement, right? So here is how you would do it. AN not convergent to 0 means there is an epsilon, right? Such that for every capital N, this doesn't happen. Now, an implication doesn't happen when the first part happens, but the second one doesn't, right? So for every capital N, there is some N bigger than, well, there's another quantifier here that is missing that I didn't write, which is a universal one for little n, right? Let me put it here. There exists a capital N such that for every little n, and now it would be the backwards one. It would be for every capital N, there exists a little n such that this first one happens, but this one doesn't. Right? So what we need to argue is that there is some interval, there is some epsilon neighborhood that such that excludes all the elements of the sequence from that point on, right? That after that capital N, so for every number, capital N, there is a sufficiently large little n that is outside of the epsilon neighborhood, correct? So in other words, we need to find out, that's now picture time. So we need to, so there's 0. We need to find an epsilon. So there must be some epsilon that I don't know. You need to tell me. We need to find an epsilon with the following property. No matter how big you pick, so for every capital N, there's an even bigger little n that it's outside of this interval, right? So you tell me a number, 134, and I tell you, okay, for 134, I can tell you that A sub 278, it's outside. Okay, it's not inside that interval. And then you go, okay, fine. How about 1,000? Okay, for 1,000, there's another A over here, which is 2014, that it's outside the interval. And then it doesn't matter. Whatever number you tell me, I'm gonna be able to find an even bigger that is outside this interval. Okay, so that's how that's the definition. And now, how do we do it with this specific one, right? How do we do it? Maybe we should draw the picture of that sequence. It's actually kind of an easy one to draw. What is it? Okay, let's see. We need 0, and let's put 1 over here and -1. That's all we need. So this is how this sequence goes. We have A1 is here, then A2 is here, then A3 over here, then A4, and then A5, and then A6 is -1/5. And then they start repeating. So this is A7, and this is A8, and this is A9, and this is A10, and so on. Right? So based on that picture, you should be able to tell me what interval should I pick around 0 such that I can find elements as big as I want that are outside. How big should I make my interval around 0?
Go with 1/10.
That will work, right? So anything such that we go inside A5 and A6 would work, right? So yeah, 1/10. So pick epsilon equals 1/10. And I can guarantee that, so then how do we do the write-up? So what I need to show is that for any number as big as you want, I can find elements that are outside 1/10 of 0. And that's easy. Yes, just pick the odd ones, right? Pick epsilon equals 1/10 for any n odd larger than 5, larger than or equal. Well, in particularly larger than 5 works. For any n odd larger than 5, we have an equals 5, 1/5, I mean. An equals 1/5, which is outside of the epsilon neighborhood. And clearly, 1/5 is not in the 1/10 neighborhood around 0, because that's the interval from negative 1/10 to 1/10. Is that clear? So that's how we show this is not convergent to 0. How about proving that it's not convergent to 1/5? That one is a bit challenging. So that was the first part. Now let's show the sequence does not converge to 1/5, right? What epsilon should we pick? Let's go to the picture right here. So now the thing is we need to center it right here around 1/5. Now the interval is centered here. So how big should we make it?
It can still be 1/10.
Yeah, 1/10 would still work. I'm gonna make it easy, and I'm gonna pick an even bigger one. I'm gonna pick 1/5. Pick epsilon equals 1/5. So if I make the interval of size 1/5, it would be this big. It would be from 0 to 2/5, right? This would be 2/5. And what are the elements that are excluded? Well, this time the elements that are excluded are the even ones, right? The A6, A8, A10, all of those guys are excluded because they are all equal to negative 1/5. So this time the proof would go like this. For any n even, now I need the even terms, with n greater than 6. Actually, 2 and 4 work too, so I don't even, but I'm gonna write it with n greater than or equal to 6, because then that way I can say what the an is. We have an equals negative 1/5. And clearly, negative 1/5 does not belong to the 1/5 neighborhood around 1/5, because that 1/5 neighborhood is from 0 to 2/5. And obviously negative 1/5 is not there, right? Okay, do you get it? Now the harder here thing would be to show that this sequence is actually divergent, right? So it's not convergent to 0. It's not convergent to 1/5. I mean, we cannot keep doing this, right? It's not convergent to, I mean, we cannot check every number one at a time. We would never finish. So there is a way to modify this argument to show it's not convergent to any number, right? So this sequence is actually, let's go back to the sequence. This sequence is actually divergent. And we'll be able to do this in a better way once we know more properties of convergent sequences, right? In particular, one of those properties is that subsequences of convergent sequences converge to the same thing. And then you could argue that here you have two subsequences, one that only has 1/5 and another one that has negative 1/5. And those two obviously are not converging to the same thing. And that would be a proof using that property. But I digress. And if you don't understand what I said right now, you don't know what a subsequence is, you're right. We haven't talked about them yet. Okay, we're gonna talk about them. The point that I'm trying to make is I'm not gonna tell you just yet why this is divergent. Okay, we're gonna do it a bit later on. All right. So instead, let's move along to the next section, which is where we're going to get properties about convergence of sequences that we can use, okay? So let's start with the first one, and it will be a very useful one, and it's this one. So this is now section 2.3, and it's called the algebraic and order limit theorems. And we're going to use this a lot. And they'll even apply to later sections. So we're often come back to these theorems. And the first thing is this definition. So it's another concept that we're going to be using thoroughly. And it's a concept of being bounded. So we say that a sequence xn is bounded if there is some capital M greater than 0, such that xn is less than or equal m for all little n in the natural numbers. All right, now in words, in an easier way to explain this, we say that a sequence is bounded if you can box it, right, with a box of size capital M, right? And so if you can find a capital M, some capital M over here, and it's negative, and you can guarantee that every element in the sequence is here, then we call that sequence bounded. So over here, say it's x1, x2, maybe x3 is over here, x4, x5, x6, etc., right? Those other ones here, I don't know what the sequence does. I don't know if it's convergent or not. I have no idea, right? But if all the elements of the sequence are between negative m and m, we call it bounded. And this is the bound, right? This is the way you can box it. It's everything is between negative n and m. Okay, a sequence that is not bounded means it becomes larger and larger, either positive or negative, right? Well, for example, sequences that are not bounded. So here's a non-example. So example, let's start first with a yes example. Example, well, how about 1 over n? The sequence 1 over n is bounded. How come? Well, because it's between negative 1 and 1, right? Using m equals 1. Because you have 1 and then 1/2, 1/3, 1/4. They're getting closer and closer to 0. So every one is for sure between negative 1 and 1. So that's one easy example. Non-example. Well, it's essentially anything that grows too much will be a non-example. So the easier one that I can think of is n, just n. The sequence 1, 2, 3, 4, 5, 6, 7, 8, etc. That one is not bounded, right? It's not bounded because of the Archimedean principle. If you think you can bound it, you know that you can always find a natural number that is even bigger than that real number that you chose, right? So this one is not bounded. Not bounded, by the way, we call it unbounded. That's the correct term. But not bounded is fine. If you write not bounded, we understand. All right, and then let's at least write down the statement of this theorem. Maybe we'll start the proof, maybe we won't, because we'll run out of time, but let's see. So this is theorem 2.3.2, and it says the following: every convergent sequence is bounded. That's nice, right? So if you have something convergent, it is bounded. And now you can use this in a backwards way, right? If you have a sequence that is unbounded, then it's not convergent, right? It's the contrapositive of that statement. And okay, let's at least talk about the idea. Maybe we'll do the write-up next class. Well, what is the idea here? Let's draw a picture. How could we prove this theorem? Well, here's how. We have a convergent sequence, right? So if it's convergent, it must have some limit, some A. So here's A, and this is going to be the limit of the sequence xn, right? And then what we know is that if we have a limit, if we go to the definition of the limit, it means that eventually, right? Remember, if we find that entry point, then everybody is going to fit within the interval that we want. So it's just a matter of picking an epsilon. And in this case, you can pick whatever you want. In fact, I'm going to make it really easy. I'm going to pick the one neighborhood. So I'm going to go one unit this way and one unit that way. And then what we know is that there is n. There is some capital N such that V1 around A contains all but finitely many of the xn, right? So in other words, everyone is in here, almost everyone. Every element of the sequence is going to be here, except a few ones that maybe are out. But the ones that are out are finitely many. That's the important thing, right? And then because they're finitely many, I will be able to find the bound. How do I find the bound, the box in which to put the entire sequence? Well, I'm going to look for either, so there's two cases. Case one, nobody is outside. There are none of these renegades outside. If there are no renegades, then my job is easy. The box is going to be 1, right? Magnitude 1 around A will work. So to find the capital M, I just pick either, I don't know where 0 is. If 0 is over here, then I pick this one. And if 0 is on the right side, then I pick this one as negative M. Either way, I can find the box. And now that's if there are no renegades. If there are these guys over here, then it's also easy because there's only finitely many of these. See, maybe there's a lot. Maybe there's 300 of them. I don't care. Finitely many. So I can look for the one that is further to the left and the one that is further to the right. And then use those to find an even bigger box, right? From negative M to M. So that's the idea. We'll write it up with care next class. And that's going to be it for today.